Good afternoon, everyone. My name is Tebetsi Lolebetse, and I'll be taking you through this presentation. So this presentation is part of our ongoing work on the Kakia Bray. So my supervisors are Professors Tafes and Kinabatu, as well as Dr. Bagai. We collaborated with Professor Chris Harris for the isotopes. So this is the presentation outline. So the Kakia Bray is located along the Molopo River, which forms the border with Botswana. It's found directly in the Molopo sub-basin. So the rural communities in this area generally depend on groundwater as their main source of water, which is mainly used for domestic use and farming purposes, which are both arable and pastoral. So this transboundary aquifer, according to a study by Peterson and Beckman in 2016, is one of the transboundary aquifers which are predicted to have a medium to a high developmental stress by the year of 2030, which is mainly due to evaporation. So that is what motivated us to carry out the study. So our objectives will be to conduct hydrochemical studies in the Kakia Bray and to determine the distribution of the groundwater quality, as well as to determine the origin of the groundwater using stable isotopes. So our methodology used mainly three methods, actually two, which was the groundwater sampling and the VES, or vertical electrical sounding. So the main reason for conducting the vertical electrical sounding was that we wanted to find out the behavior of the dolomites as you move towards the border. So for the groundwater sampling, the method that was used was depth integrated sampling. And samples, before collecting samples, we made sure that we purged the boreholes for 10 to 15 minutes. So from the samples, we collected cut iron samples, anion samples, as well as isotope samples, which were collected using these centrifugal tubes. So the cut iron samples were acidified using nitric acid, and the anion samples were not acidified. So the cut ions were analyzed at the geochemistry lab at the University of Botswana. The anions were analyzed at the Okavango Research Institute in Maung in Botswana. And as I have mentioned before, the stable isotopes analysis was conducted in UCT in collaboration with Prof. Chris Harris. So figure 2.1 shows the distribution of our sampled boreholes within the area. And may I add that we were using existing boreholes. So our VESs formed a profile which was roughly 26 kilometers with an interstation spacing of 5.29 kilometers. So the first frame shows one of the VES we conducted, which was VES 6. So the VES AB/2 spacing ranged from 1 to 350 meters. That is for the stations which are found on the edges of our profile. And for the middle VES stations, we used an AB/2 spacing of that range from 1 to 300. So the photo in the middle shows the preparation of the samples prior to putting them into our ICP unit for elemental analysis. So these are the results that we got. So what we have seen from this data set is that we see a variation of EC and TDS, which generally varies from this fault here, which actually partitions our transboundary aquifer into two limbs, the northern limb and the southern limb, with the highest EC and TDS reading found along the boreholes, which were actually along the fault. So what we have generally saw is that the trend for TDS and your EC generally reduces as you move from this fault moving towards the border. So what we've also noticed is that there are some boreholes which showed concentrations of chloride and sulfate which were relatively too high, which we ended up thinking that it may actually inform us that there might be some regional water mixing with our water. So the boreholes in question are boreholes ZF7, ZF8, ZF9, 10, and 11. They generally show high concentrations of sulfates and chloride. So the most dominant major ion that we found was bicarbonate, which actually verifies that carbonate dissolution may be the most dominant chemical process in the area. So from table 3.1, we managed to derive around 11 water types from the boreholes that we sampled, with the predominance of calcium magnesium bicarbonate type and sodium magnesium calcium bicarbonate type. So onto the geophysics results. The three sections that you see are VESs collected from the VES0 on this frame here is from the VES station which was closest to the border we share with South Africa. And then VES4 here on this end is the most inland station. So these are the furthest points of our profile. And then VES3 in the middle here shows the middle station that we actually took in the profile. So what we can see from this data is that most of our data is a combination of Q and H type resistivity curves, which tend to show us that there is this consistent lower resistivity layer in our velocity models, our VES models. So this low resistivity layer is quite consistent throughout all our VES models, which tends to suggest that this may be the dolomites that we are actually looking for. So the highest error that we actually recorded from our VESs was 2.86, and the lowest error that we got was 1.98. So in order to understand the groundwater evolution of our transboundary aquifer, we prepared this Piper diagram here, which generally shows that our samples fall within the magnesium bicarbonate type, with a bit of variation in some of these boreholes which are found on the upper limb and along the fault. And then in terms of the anions, we see that most of our samples fall within the bicarbonate type, and some of them falling within the no dominant type, and one borehole which is ZF8 falling within the chloride type. So in order to understand our models, we produced a graphical match of our calibration VES, which was VES4 from the previous slide, with our reference borehole BH9140. So BH9140 was selected on the basis that it had intercepted quite a significant portion of the dolomites, which seemed to extend more than 200 meters. So this plot here shows the correlation of our stable isotopes. So the main criteria of selection of boreholes for sampling for isotopes was we wanted to sample boreholes which have intercepted the dolomite. So for analysis of our results, we used the global meteoric waterline, duly because none of the local lines that we have in Botswana would fit this data set, as most of them were steep, mainly plotting around this area. Hence why we resorted to using the global meteoric waterline. So what we can see here is two clusters of data which are parallel to a global meteoric waterline. So what we can tell from this data is that our data is generally from a meteoric origin. However, our data sets are quite widespread, and this may suggest that there might be multiple sources of recharge which recharge at different rates. So as a summary, we actually intend to integrate all these results in order to come up with one final conclusion that will inform us on what is actually happening on the transboundary part of this transboundary aquifer. And we intend to produce a pseudo-section using our VES sections in order to appreciate the continuity of our dolomites from the from the Botswana side into the South African side, and to determine the thickness of our dolomites. So these are my references. I'd like to acknowledge my sponsors for making this presentation possible, as well as making it possible for this research to be undertaken. Thank you.
Thank you. Thank you very much, particularly for sticking to time. At this point in time, I will ask for quick comments, questions. Yes, sir?
Regarding chloride and sulfates, you said some of the boreholes, the results from the test, exhibited uncharacteristically high levels of these two anions. So the first part of the question maybe informs if the second part is relevant at all. Were these on the lower or the upper limb of your fault?
Okay, so most of these boreholes were on the upper limb of the fault. However, the highest reading of the sulfate and the chloride was a borehole which was exactly on the fault.
Okay, and so here's my question. Why do you draw that conclusion that you suspect that there could be mixing of waters, you said, because of these high levels?
We say that because we have come up with the thinking that our fault may be actually acting as a conduit that is actually bringing in these regional waters which are actually mixing with the water within the transboundary.
Okay. Yeah, for the rest, I think I'll find you afterwards.
Thank you very much.